Hello and welcome to another episode of Conservation of Momentum. This time around we're going to deal with perfectly elastic collisions. And here are examples of the outcomes of a perfectly elastic collision. Let's say that we have two masses and they are identical. When mass 1 moves and mass 2 is stationary, well, the moment they bump into each other, it kind of behaves like billiard balls. Mass 1 stops and then mass number 2 starts to move. And again, this only happens if they share the same exact mass. Well, what if mass number 1 is much bigger than mass number 2? On your marks, get set, go! Now take a look at mass 2. You can see that it's moving much faster than mass 1 in the first place. In fact, theoretically speaking, if mass 1 is much bigger than mass 2, the tinier object can travel as much as twice as fast as the first mass. Let's take a look at case number 3 now. This time around, we have a tiny little guy compared to a big guy. Ready, little guy? On your marks, get set, go! And you'll see the little guy just bounces right off the big dude. Now, if the big dude was as big as the Earth, the big dude will more or less be stationary. But you'll notice in a perfectly elastic collision, what will happen with a small object is that it may end up bouncing off and traveling in the exact opposite direction at the same speed it approached it at. Want to see this one more time? Sure, let's rewind this right from the beginning. Alright, so this is the case where the two objects share the same exact mass. Now, one thing I want to point out is that I shouldn't show them rolling, alright? But I think in our minds we're just so used to seeing objects roll. Because when an object rolls, it also has another form of momentum, which is angular momentum, and that's beyond the scope of this course. So let's just imagine these two objects as just, stationary objects gliding on a frictionless surface. Alright, so yeah, in the case of m1 is equal to m2, this will exactly happen. So if I had squared objects on a frictionless surface, this outcome will happen for sure. Just like if the first object was much larger than the smaller object, the first object will continue to move at roughly the same velocity as it was before, but the little object can travel up to as fast as twice as the speed of the original object. And if we flip the rules around, you'll know that the little guy always ends up losing. And that's just an end reality. Okay, let's see some real-life examples that we can find on the good old internet. Here we go. Alright, one thing I want to say as a disclaimer is make sure you don't do any of this stuff at home. I think these guys are trained professionals that you can find on the internet. Alright, so in the first case, we have these two friends and, well, can you guess what their masses are? You'll notice that friend number 1 on the left, which is m1, comes rushing to m2, and right after the collision, m1 is stationary and m2 starts to move. So you can probably guess that in this case over here, these two friends share roughly the same mass. How about in this next case? Alright, friend number 1, oh boy, it looks like he's had a lot of stuff to drink. Alright, on your marks, get set, go! Alright, and you'll see both friends end up moving in the same direction afterwards. The only way for this to happen is if mass 1 is greater than mass number 2. What about case number 3 now? Ready, friends? On your marks, get set, go! Boing! Alright. So, can you predict who's the heavier friend? If you guess the friend on the right, you are correct. Well, since it's the internet, I'm sure they've tried other adventures like these ones here, so let's take a look. Okay, you can probably guess who has the lower mass. How about this one over here? That friend versus that friend over there. Ready to go? Oh, it's going to be a rather unfair match. And I think you can already predict what the outcome's going to be. But what else do university friends with guitars in the libraries do other than, yeah, that? Now remember, even though kinetic energy may not be conserved, momentum is always conserved. Ready, friends? Here we go. Boom. Momentum is always conserved. Got that, buddy? And yeah, you can probably find a lot of other videos on the internet that have to do with stuff like this. I do have to tell you a reality is that it's not always fun like that. There is a grim reality where yeah, if you want to turn your head around, by all means, but look at the relationship between a truck and a car. And you can see the poor little car flying. As we discussed earlier, if the first mass is much greater than the second mass can travel as much as twice as fast as the first mass, and that's a disturbing reality. So why is this always true? Well, let's go and find out the formulas that predict this. All right, we're talking about a perfectly elastic collision, and in these cases, kinetic energy is conserved and momentum is conserved as well. To make our calculations a bit simpler, let's just assume that the second object is at rest, and this will make a smaller formula at the end. All right, and we'll deal with cases where V2 is not equal to 0 later on. Okay, so if kinetic energy is conserved, then we know that Ek at the beginning is equal to Ek at the end. And again, since the object number 2 is at 0, that's why Ek for object 2 is at 0 joules. To clean this up, let's multiply everything by 2. And then we can bring this term over to the left-hand side and factor out m1. And we'll pause there for now. Next, we'll move on to the world of momentum, where momentum's also conserved. And again, since V2 is at 0, that's why object number 2 at the beginning is at 0. We can do something very similar as the previous one. We'll take this term and we'll bring it over and factor out for m1. And that way we have two formulas that look very similar to each other, all right, between these two over here. So we can solve, using one of three different methods. We can either solve by elimination, by substitution, or game plan number 3, by division. So if you divide equation number 1 by equation number 2, it will boil down to this formula over here. It's rather nice and clean. And optionally, if we want to isolate for V1, what we need to do is we need to take V1, the previous apostrophe one, bring it over to the other side, and we end up getting the formula on the right. Okay, so we have a formula isolated for V2 apostrophe, and we have a formula isolated for V1 apostrophe. We can then sub it back into the formula. This formula over here, and rinse and repeat again for this one afterwards. And by doing that and carefully rearranging it, it will derive out to these two equations here. I suggest you try it out for your own sake, but just to let you know, these two equations, they will be available for you on any future quiz, test, or exam, so no, you don't have to memorize it. Just keep in mind that these two equations are only good if V2 is at rest. Okay, so let's go through some sample calculations then. Let's say that Eric has a crush on Francine, and to show his affection towards Francine, he decides to run and give Francine a chest bump while she was standing and chatting with her friends. Now, if Eric was running at 5 meters per second and it has a mass of 70 kilograms, and Francine has a mass of 50 kilograms, then, what will happen afterwards? All right, so you have mass number 1, which is Eric, and mass number 2, which was Francine. Okay, well, let's try this out. Starting off with your givens, what do you know? So mass number 1 is at 70 kilograms, and mass number 2 is at a smaller 50 kilograms. And since mass 2 is less than mass 1, you've already seen the outcome. What's going to happen afterwards is that their velocity after the fact, those continue to move in what is defined as the positive direction. All right, so V1 is at, 5 meters per second? And yes, V2 is at 0 meters per second, and we can find our V1 apostrophe, and we can also find our V2 apostrophe as well, just by using these equations on the right. Okay, let's start with the first one. V1 apostrophe is equal to mass number 1 minus mass number 2 divided by mass number 1 plus mass number 2 multiplied by the velocity of object number 1 at 5 meters per second. You can rinse and repeat for V2 apostrophe as well. So double of the 70 kilograms divided by 70 kilograms plus 50 kilograms, all multiplied by 5 meters per second. And once you calculate through that, you'll get the answers of 0.83 meters per second for the big object, and the little girl, unfortunately, will travel at 5.8 meters per second, still in the positive direction. Okay. Well, what if things was turned the other way around, and Francine was the one running towards Eric? Try it for yourself. And when you're ready to see the answers, continue playing the video. Alright, so before we get to the answer, keep in mind that this time around it's a tiny object competing against a large massive object. Alright, and again, anytime that this ends up happening, little guy will lose. What will happen is the little guy will ricochet and bounce in the opposite direction, and yeah, the large object will move in the positive direction, but not as quickly. Did you guys get to this answer? Awesome. Okay, what about case number C? Let's say we're back to the original story. However, Francine also wanted to say hi to Eric, but she was running in the opposite direction. What's going to happen? Again, with these equations here, it doesn't factor in for V2, so how can we take care of that? Well, the answer to this isn't way too challenging. Instead, what you have to think about is frame of references. Keep in mind that this entire experiment is happening from an inertial frame of reference. There is nobody accelerating. Kind of like me here on the airplane. As I drop the object, you'll notice that even though the plane is flying blazingly fast forwards, the object still falls vertically. And that's because we're in an inertial frame of reference. Again, whenever you're in that situation, it doesn't matter how fast or how slow you're going. As long as you're maintaining uniform motion, the outcome will be identical. And that's the hack in solving these problems here. What we'll do is that we'll change our frame of reference. Instead of staring at these two people running towards each other from afar, instead we just keep our eyes focused on object number 2, making V2 appear to be stationary. How do we do that? Well, since V2 is at negative 3 meters per second, to make it stationary, we need to adjust our frame of reference by making ourselves now move at 3 meters per second. So negative 3 plus 3 will net to a value of 0. And we must also factor this in for the first object as well. So the first object, or Eric, he was moving at 5 meters per second. Now we need to add 3 meters per second to it, and then that will get us 8 meters per second. Now that we've changed our frame of reference, we can now use the formulas one more time. So V1 apostrophe is equal to mass 1 of, I believe it was Eric, minus Francine, all over 70 kilograms plus 50 kilograms, times, this time around, 8.0 meters per second. 7 minus 5 gives us 2, so it's 2/12 times 8, and I get an answer of 1.33. Again, this is from the frame of reference of object number 2. All right, we need to convert back to ground afterwards. I'm just going to pause there for now. I'm going to move on to the second formula. V2 apostrophe is equal to 2 times mass of object number 1 divided by 70 kilograms plus 50 kilograms times 8 meters per second. Divided by 120. There you go. Multiplied by 8, and that will give me 9.33. That's better. Now remember that initially I had to add 3 meters per second to nullify things? Well, now I have to do the opposite. So if I need to change the frame of reference of the ground, I now need to subtract 3.0 meters per second to change the frame of reference to ground. So 1.33 subtract 3 will give us negative 1.67. And for the second object, 9.33 subtract 3.0 meters per second will drop down to 6.33 meters per second. And that's how you'd solve these problems. You first change the frame of reference to the second object such that it's stationary, and then don't forget to convert back to the frame of reference of the ground afterwards to get to the answer. And that's it. I guess before we move on, I just want to emphasize one more thing, which is, why was it true that when m1 is equal to m2, that whatever happened, happened? Well, let's take a look at the formulas here. If m1 is equal to m2, then what we end up happening is that we have v1 apostrophe is equal to 0 over a number. And 0 over any given number is equal to 0 meters per second. So that's what happens to the first object. After it collides with the second object, it's now stationary. What happens to v2 afterwards? Well, we can go through that math as well. Again, if we assume that m1 is equal to m2, then what we have effectively here is m plus another m, which gives us 2m downstairs. 2m upstairs divided by 2m downstairs, that gives us an answer of 1. 1 times v1, so v2 apostrophe is equal to whatever v1 was originally. And that's what happens every single time when they share the same mass. Well, what if m1 is much, much bigger than m2? Alright, so if m1 is much, much bigger than m2, then you can imagine m1 being a number that's, a number like infinity. And m2 is being so small that it's negligible. In the denominator, now we have an infinity plus a negligible number. And an infinity divided by infinity approximates to 1. Alright, so what happens is that your v1 is still equal to v1 whatever it was before, roughly. I mean, it'll be slightly less, but it's more or less there. But now let's see what happens to v2 apostrophe. Alright, 2m1 over m1 plus m2. Again, if m2 is really small, it'll be negligible in the big picture. So we really have double of infinity divided by infinity, which then will give us a ratio of 2 to 1. So v2 apostrophe will be double of whatever v1 was before. That's where we got that proof from. I encourage you to try out the other case now, where m1 is much less than m2, and see if it matches up with the results that we discussed earlier. One last thing, if you want to confirm whether something is perfectly elastic, then what you need to do is that you need to calculate out the total momentum before and see if it's equal to the total momentum afterwards. And then you need to rinse and repeat again with regards to kinetic energy. As long as these two traits are true, then an object is experiencing, or collision is experiencing, a perfectly elastic collision. That's it for today, so your homework is page 239 as well as 248, and I'll see you in the next adventure.